Hi, I'm Alan Downing. I'm the Senior Director in charge of AQ development at Oracle. I've been at Oracle since 1993. I'm here to talk about AQ JMS for better performance. Two members of my team are available on the live chat if you have any questions during this presentation. Oracle's Safe Harbor statement says that this presentation is for information purposes only. So what I'm trying to accomplish in this talk is to highlight some of the key points of the presentation, give the background behind AQ JMS, and to provide technical details of sharded queues as well as some performance numbers. In 12C, we're introducing JMS Sharded queues. These are a new type of queues that can be used as an alternative to your existing non-sharded AQ JMS queues. If you're fine with your existing non-sharded queues, there's no need to change. But if you're finding that the existing non-sharded queues need to have higher throughput, for example, more messages per second, especially on a rack cluster, you should consider moving to JMS Sharded queues. If you want to use up less system resource consumption, especially CPU, you should consider moving to JMS Sharded queues. If you want to better utilize your rack instances and have many enqueuers and dequeuers on each of the rack instances, you should consider using JMS Sharded queues. If you have a large number of subscribers and finding that your existing non-sharded queues are not satisfying your performance needs, you should consider moving to JMS Sharded queues. Earlier in 2015, we introduced two new white papers. There's a new white paper on JMS Sharded queues. All the performance numbers that I'm covering in this presentation are covered by that white paper. In addition, we've revised the advanced queuing white paper and tutorial and covered new best practices. If you're one of the customers using the advanced queuing and rack white paper and that provide guidelines on scalability and performance for the non-sharded queues, you're probably one of the people who should be considering using JMS Sharded queues. I'd like you to kind of throw away that old white paper and read the JMS Sharded queue white paper. So that's some of the key points, but what is AQ? Oracle AQ stands for Advanced Queuing. It's the messaging and notification solution for the database. It provides JMS 1.0 support. It's our most popular API to AQ, but there's also PL SQL APIs, OCI APIs, JWC APIs, and .NET support. By being integrated with the database, we can provide some optimizations that you as a customer could not do on the database directly yourself. So it has some performance optimization in non-sharded as well as sharded queues. AQ has a messaging gateway that interfaces AQ with IBM MQ Series and TIBCO Rendezvous. AQ is part of the infrastructure of Oracle Streams. It provides some of the basis for the database capture and apply of streams. But these days, Golden Gate is the replication solution that's preferred, but AQ is still the preferred messaging and notification solution for the database. Let's give a brief history of AQ. AQ introduced single consumer queues way back in Oracle Release 8.0. Release 8.0 is also when objects and abstract data types was introduced, as well as index organized tables and partition tables. AQ uses ADTs as part of its PL SQL APIs, and it uses IoTs as part of its non-sharded queue architecture. In Release 8.1, AQ introduced multi-consumer queues. Multi-consumer queues are analogous to JMS topics, but it actually predates JMS. As a reminder, Release 9.9 is when Oracle RAC, or Real Application Clusters, was introduced. In 9.2, AQ provided support for JMS 1.0, It's also the release when Oracle Streams was introduced, and as part of its infrastructure, AQ was renamed as Oracle Streams AQ. And in the 10G timeframe, AQ was enhanced mostly with Oracle Streams in mind. Around this time is when the Golden Gate acquisition happened, and Golden Gate became the strategic direction for replication. And AQ concentrated more on the performance optimizations of messaging and included things like better integrated JMS client support. As a result of the Golden Gate acquisition, AQ was renamed back to Oracle AQ because it continues to be enhanced, and that's in evidence with the AQ JMS Sharded queues, which has major enhancements, especially for things like rack and JMS, both of which AQ predates. So AQ continues to live on and has a bright future. AQ is a very popular feature. It's heavily used within the database itself. It's also used by Oracle applications as well as customers. Let's just cover some of the database use cases. As explained earlier, it's being integrated with Oracle Streams. Database change notifications is integrated with AQ. It uses AQ for its PL SQL callbacks or to notify the applications of changes like DML or DDL to table. Database alerts such as instances going up or down also uses AQ. The database scheduler is integrated with AQ. It uses event-based jobs and rule-based job chains internally, and AQ itself uses the scheduler as part of its propagation. Fast application notification uses AQ before 12.1 to get notifications such as instances going up and down. Data pump uses AQ internally. EM uses AQ to generate alerts such as not meeting certain performance thresholds. The Oracle Messaging Gateway provides integration with TIBCO Rendezvous and IBM MQ Series. Audit Vault, Data Vault uses AQ features such as the rules engine, and there's more. In addition to AQ usage by database features and products, AQ is heavily used outside by Oracle and customers. Oracle WebLogic Application Server has a JMS foreign server framework that has support for AQ JMS. Oracle Applications heavily uses AQ. There's many queues inside of eBusiness Suite, Fusion Applications, Oracle Retails, and others. This usage of AQ has increased with the Oracle Cloud. Many services use the database to hold the state, including the messages. So if there is a reason for the database to fail over, not only is your table changes failed over, but the messaging that is associated with that those changes are also failed over atomically. Externally, AQ is used by many customers for all sorts of use cases. Here's some of them that are listed here: workflow type stuff, asynchronous processing, application integration, message-based logical replications, and many other use cases. Oracle has multiple JMS implementations. So when is AQ JMS a better fit than, let's say, WLS JMS or other JMS implementations? Vivek Maganti at a previous Open World gave a presentation about this, and this slide is a summary of some of his key points. So if you're counting on the guarantees offered by an Oracle database backed messaging system, such as DataGuard for high availability, AQ, of course, is a really good match. Internally, the cloud uses data guard so that tables and messages are failed over atomically. AQ allows SQL access to queues, so if you want to do select of the data within queues, you can do that. AQ notifications are very heavily used. You may use JMS to enqueue a message, and then you want it processed through a AQ PL/SQL notification or callback, and this will run a PL/SQL procedure to process that message. WLS has optimizations so that two-phase commit is not required when you are combining table changes with messages. Instead, these are done within a single transaction. AQ can handle a very large concurrent message volume, and even more so with sharded queues. If you have extremely large message backlogs and you can't throttle the producers, AQ, by being database backed, can store a ton of messages. If you have very large message sizes, AQ can handle it because it has support for secure files. Before moving on to 12c and sharded queues, I wanted to highlight some of the performance and scalability optimizations in 11. One of the key ones is the native JDBC thin driver support for AQ. It greatly reduces the amount of round trips between the client and the server. We've improved diagnosability by adding better error messages and also more runtime views, and these can now be monitored via a PL/SQL package. We've improved the scalability of event notifications and messaging gateway. We've now been integrated with the scheduler. There are many important performance optimizations. One of the key ones is the index coalesce. If you had a very heavily enqueued and dequeued queue, you would periodically need to coalesce the index to improve the performance. Now, this is all done automatically by AQ at near the optimal time. We've done optimizations for DQ by first messages and also just DQs in general, as well as subscriber management. In recent years, we've noticed a trend that is AQ is being used on Exadata and other high-end hardware configurations, often in a dedicated manner where messaging is the main purpose of the system itself. And in these configurations, we notice that the non-sharded queue architecture that used indexed organized tables had some limitations. So we've introduced in 12c sharded queues to get around these limitations and to scale much better. So what is AQ JMS sharded queues? Well, a sharded queue is a single logical queue with many shards. And a shard is a way of maintaining higher concurrency and throughput via horizontal partitioning. You may have heard of sharded databases that try to get higher concurrency and throughput by horizontal partitioning. Well, this is the messaging equivalent of that. So how do we implement these shards? Well, first of all, we need to maintain the session ordering as required by JMS. So if you enqueue do multiple enqueues from one session, you want to make sure that these messages are dequeued in the same order, and we do that by automatically managing the session affinity to shards. We use table partitioning to implement shards, and we automatically manage these table partitions. We do this in a couple ways. One way is we make sure that there's partition instance affinity. So for example, if enqueues are happening to a shard in one instance, we make sure that the same table partition is not updated simultaneously by another instance. So there's no block pinging going on within the partitions that implement the shards. This avoids a lot of contention at the block level and can lead to much better performance. In addition, by automatically managing the table partitions, we can do bulk operations on these partitions, and we can manage the creation and removal of these partitions. In fact, sharded queues implement all the lessons learned that we've had over the years with AQ non-sharded queues. We've learned a lot of lessons, and we've implemented sharded queues with these lessons in mind. A couple pictures might illustrate how sharded queues work a little better. This slide shows a single logical queue, an abstract representation. JMS Sharded Queues tries to present a single logical queue to the users. In this case, you have enqueuers going into one side of the queue, and dequeuers dequeue from the other side of the queue. This would typically be in, first out ordering. So sharded queues, though, the actual implementation of this doesn't look really like this at all, and I'll show that in the next slide. But non-sharded queues, this is a fairly reasonable representation of the architecture of non-sharded queues as well. Non-sharded queues use index organized table, and the gray box represents the table. The red box represents the index of the messages. Enqueuers go into one side of the index, and dequeuers take messages out of the other side of the index, and those sides of the indexes can actually turn into points of contention, especially on rack. If you have enqueuers on different instances of the rack, they will be trying to enqueue and insert messages into the same block of the index. Similarly, on the dequeue side, they're trying to dequeue and possibly clean up the messages on that side of the index. So these could be hot spots that can slow down performance, especially on rack or Exadata. And this is something that architecturally we're trying to avoid in sharded queues. However, we still try to present sharded queues, provide the same JMS guarantees of session ordering, but we do it very differently. This figure gives a better representation of the physical queue of sharded queues, where partitions are mapped to shards with instance affinity. Here we have 3 instances. In some way, there are different logical queues on these different instances. These logical queues are basically the shards. In this particular example, there are 3 shards, 1 for each instance. Enqueuers would be enqueuing messages into one side of the shard, and dequeuers would be dequeuing from messages on the other side of the shard. Now, these shards are broken up into sub-shards, and those are little sub-boxes inside of the that are gray for each of the instances. And these boxes are actually done by partitions. So the gray boxes are the gray box is a partition table. There is actually one partition table for all 3 instances, but the partitions within that partition table are assigned to an instance. So when an AQ session comes along, that session will be connected to an instance. At that instance, that session will be assigned to a shard. That shard will be assigned partitions to store the messages for that shard. Similarly, DQers, DQ sessions would connect to an instance, and they would be assigned a shard that has affinity to that instance, and they would DQ from subpartitions on that shard. In a simple case, let's say a single consumer queue, also known as a JMS queue, you would like to have a whole bunch of NQ sessions, each assigned to different instances, connecting to different instances, and they NQ into each one of those instances. Similarly, we would like to have a whole bunch of DQ sessions that are distributed around the different instances, and they would be assigned to shards on that on each one of those instances. And ideally, a message that's queued into instance 1 would be dequeued by a session on instance 1. So that way you could even play tricks. We have a message cache, for example, and that message cache forms a queue specific index or represents a queue specific index. And messages that are enqueued into a shard might be dequeued immediately by a dequeuer session, and in such a way that the dequeuer never actually has to run a select against the partition table. So by having the instance affinity, enqueuers and dequeuers may all be working on a single logical queue that has blocks that are within that instance. Now, this is a kind of the best case representation. Things can get more complex. Let's first talk about multi-consumer queues. They're also known as JMS topics. In this case, you would have subscribers assigned to the sharded queue. Ideally, what you do is for each subscriber, you would have a whole bunch of DQ sessions, and these DQ sessions would be distributed across the different instances. So once again, enqueuers would enqueue messages that would be dequeued by sessions on the same instance, keeping things all local and keeping things efficient. But, you know, this isn't always an ideal world. You might have a case where one of the subscribers only has a single session dequeuing from a single instance. Let's say that this single dequeuer is connected to instance 3, but at the same time you've got enqueuers enqueuing to each one of these instances. Well, if you see the little arrows on the right hand side of the gray boxes, this is what we call the cross process. These forward messages that are enqueued into one instance and will forward them on to other instances, such as instance 3's dequeuer. And we will try to keep these all in memory and inside the message cache if we can. So once again, you don't actually have a situation where you write into the same block from two different instances. We try to make it so that all writes are local to a single instance within a shard. Similarly, we avoid as much as possible read-read conflicts by using the message cache. So by doing this architecture, each one of the instances performs very efficiently with enqueues, dequeuers all local. We also get to use partitioning, and by doing partitioning, it lets us do more sophisticated memory management. It also lets us do bulk operations, potentially like partition truncates and partition reuse and reallocation. So a partition that has been emptied out by a dequeuer could then be reallocated to be so more messages can be enqueued into that same partition, possibly on the same instance. So, although sharded queues provide a single logical queue abstraction, underneath it's actually a lot more sophisticated. So delving down into the automatic partitioning management, enqueuers are mapped to a shard to maintain the session level ordering. Dequeuers have affinity to shards. You may have multiple shards on an instance. So there's multiplexing between shards on an instance based on enqueue time. So if there's a single dequeuer and on an instance and multiple shards on that instance, it will multiplex between the two and figure out which one has the let's say oldest enqueue time for first in, first out. We also load balance between the dequeuers, so we try to spread out the dequeuers across the shards. We do this automatically. Now, the partitions themselves, we manage that automatically as well. We add the partitions when needed. Partitions can be reused. They can be truncated. And we do this all automatically to get the best performance. After all the messages in a partition are fully dequeued, we can truncate the partitions, and this avoids the table high watermark growth. And this is one of the things that we optimize for IoTs in 11G, because in there we had to periodically coalesce the index. Well, we don't have to do that when we truncate a partition, because that gets rid of the coalescing type problem. And once again, we use partition tables. We don't use IoTs. And we don't use a regular B tree here to maintain the ordering. Re-emphasizing how we optimize for rack, the best practices are to have enqueue and dequeue threads at each instance for each subscriber. And furthermore, you want to make sure that you have sufficient dequeue threads to keep up with the enqueuers. And in sharded queues, dequeuers are typically faster than the enqueuers. And you'll see that in some of the slides later on. That's kind of the opposite of what might happen with the non-sharded queues. These are partition tables to store the sharded queues. So you can add indexes, but you definitely should avoid using global indexes, because that could lead once again to the hot blocks, and you really want to avoid that on rack. Instead, all indexes should be local to the partition. Sharded queues make sure that the shard ownership is associated with an instance. You enqueue to a shard only at a single instance. We'll make sure that all dequeues are local if at all possible. But if it's not possible, we have a cross process that transfers messages between instances, but only if it's necessary. Next, I want to look more into some of the components of sharded queues. We've already talked kind of how the automatic management of the shards and partitions are done. We've already talked a little bit about rack. But I'd like to go into more details about the message cache, the JMS support, some of the optimization, the rules engine, and the subscriber management. Architecturally, the components can be arranged as follows. You have the JMS NQ DQ drivers at the top layer. These are customer facing, as are the admin operations. Also at the top is some of the time management and background processes. Next, we emphasize the message cache. We put it in red just to show that this thing is everywhere. Anything that can be kept in memory will be kept in memory. And it's integrated with all the components in the next layer, the rules engine, the subscriber management, and the shard management. At the bottom layer, we have the actual tables, like the partition queue table. We have the DQ log table that is used to log DQ information very inexpensively. We also have the cross process to share messages across the instances. The message cache plays a key role for sharded queue performance. The message cache is allocated from the streams pool, so to get the best performance, you need to allocate streams pool to the message cache. We effectively use the message cache as a queue optimized in-memory index. If at all possible, we will keep the payloads in memory. So small payloads that are, let's say, less than 2K will be stored inside of the message cache if there's space. Large payloads, let's say those that are in out-of-line secure files, those won't be stored in the message cache. However, we try to keep the message properties in the cache for these larger payloads. This way you can have the rules engine evaluate the JMS selectors using the in-memory message properties. So we don't have to necessarily run a select statement to figure out which messages are applicable to particular subscribers. Very importantly, we keep this message cache transactionally consistent with the partition tables that are used by sharded queues. While in 11G, non-sharded queues had much improved JMS support by the drivers, the fact remains that non-sharded queues predated JMS, and there's a bit of an impedance mismatch in a few places, such as non-durable subscribers. So for sharded queues, we designed things from scratch with JMS in mind. So things like non-durable subscribers are much better supported. JMS payloads, they don't use the AQ JMS ADT that was in 11.2. Instead, it uses the scalar data. All 5 types of JMS messages can be stored within the same queue or topic. We can support unlimited user properties with unbounded values. JMS selectors are optimized for fast rule evaluation using the message cache. Also, we handled JMS message priorities natively. We've tried to implement very intelligent NQ and DQ optimization. So if you allocated streams pool by setting the streams pool size for the message cache, we will DQ from memory. We won't do a select. So we can effectively emulate the performance of in-memory message queues with a database-backed messaging system of AQ. So by extensively integrating with the message cache, with the rules engine, and more. Also, everything we can move into the background processing, we move to the background processing, such as the partition and operations. When you do a DQ, we don't have to actually delete a row. Instead, we actually just have to insert a tiny little bit of data into the DQ log, and then we can do bulk operations and the partition operations later on. We also optimize the subscriber support. There's not separate rows for each subscriber. Instead, what we have is a optimized bitmap for subscriber information that's stored inside of the message cache. And the rules engine is also integrated with the message cache. So altogether, we try to keep things as in memory as possible. DQ by correlation ID or JMS properties can often be evaluated without using SQL evaluation. Instead, it uses the AQ rules engine, which operates against the message cache directly. Now for 12C, the rules engine has been enhanced to be able to faster evaluate many SQL 92 expressions, and such as bit and seal and the other operations mentioned here. Sharded queues try to absolutely minimize the amount of overhead necessary to maintain subscriber information. First, we provide native support for non-durable subscribers. In addition, we have a in-memory subscriber bitmap and on-disk bitmap that avoids maintaining a separate table for the subscribers. We also have intelligent use of a DQ log and message cache operations that absolutely minimize the amount of SQL that need to be done. As a result, things are a lot more efficient for sharded queues than non-sharded queues, and you can handle a whole lot more subscribers. In addition, I want to point out some of the best practices, and that's to have DQers for each subscriber on each instance. That way you can have NQs and DQs local to each instance. Now that you get the gist of how sharded queues work, let's go into details of actually how they perform. Now, what we have here is a graph that shows the DQ throughput of a JMS queue for both sharded and unsharded queues. Now, this is a simple test where we have a number of NQ threads and DQ threads, and these number of threads are incrementally increased for the JMS queue and on an Exadata X4-2 database machine, and we keep on increasing the number of threads until the performance tails off. The message size is a 512 byte payload, so this is not a toy payload that you might see in other folks' benchmarks. We have 10 NQ or DQ operations in each transaction. This is not uncommon. This is matches how many of our customers, or even internally how AQ is used. Often there's a lot more overhead than just the AQ messages themselves. There's operations to tables, and then AQ is used as kind of a asynchronous passing off of control. This is a log graph, but sharded queues scales linearly with no regression as more instances are added until you get to about 32 concurrent NQ and DQ processes. The bottleneck for the sharded queues was a combination of the transaction commit overhead and the partition maintenance overhead. So, for example, truncating a partition might invalidate some of the cursors that would need to be reparsed. A sharded queue, the DQers were able to keep up with the equivalent number of NQers in the JMS queue for up to 76,000 DQs per second. On the other hand, in contrast, the unsharded queues didn't show a large increase of DQ throughput as more threads or instances are added. In fact, unsharded queues perform best on a single rack node with a throughput less than 8,000 messages per second. That's in the kind of bright red line there. So, as we recommended in the earlier white paper for non-sharded queues, you're better off if you keep all your NQing and DQing of AQ to a single instance. But that's not true when it comes to sharded queues. Now, the reason that the unsharded queues don't perform as well is, as expected, the global index contention. So you'll see things such as buffer busy or global cache waits in an ADDM report. Within a single node, the CPU was the resource bottleneck for the unsharded queues. When possible, unsharded queues really should use the instance affinity feature so that all the NQs, DQs, and background processes are all on the same instance. So the scalability of sharded queues is across the rack instances is much better than the unsharded queues. Next, for the same test, let's look at the NQ throughput for the JMS queue. And you can see it behaves similarly as the DQ did. The sharded queue scales well with the rack instances as you increase the number of rack nodes. In contrast, the unsharded queue performs best on a single node, and the DQs do not keep up with the NQ rates when the number of queues and DQ threads for the unsharded queues were kept the same. An interesting result of all this test was that the sharded queues could DQ over 4 times as many messages per CPU compared to the unsharded queue at higher loads. In addition, the sharded queues spread the workload well across the instances, and the latency of the DQs in the sharded queues was typically less than a millisecond. Okay, that was JMS queues. How about JMS topics? Well, a JMS topic is a multi-consumer queue that's typically used for published subscribed applications. So in this variation of the benchmark, we configured 10 subscribers for each of the 512 byte messages. So if you had 4 instances and 4 NQers and 10 subscribers, 1 NQer is connected to each of the rack nodes, and each node has 10 DQer threads with each of the threads for a different subscriber. So that's basically the configuration. Next, about the results. So with 10 subscribers for each of the NQ'd messages, sharded queues achieved approximately 100,000 DQs per second. And it had the same bottleneck of the commit overhead and partition management. Unsharded queues had the overhead with the global index contention and performed not nearly as well as the sharded queues. And in addition, the sharded queues used less than half the CPU consumed of the non-sharded queues. It's pretty easy to change the benchmark to get rid of the commit overhead. In this slide, we get rid of the commit overhead bottleneck by batching together in each transaction 1,000 operations. So you would do 1,000 NQs and commit, or 1,000 DQs and commit. And that's kind of overkill, but the point was to try to get rid of the that bottleneck and leaving the partitioning management overhead. And you can see the results here. This is combined NQ and DQs across all the subscribers, and in this one you end up with about 150,000 combined NQ and DQ operations per second. Now customers often come to me with like operations per hour, and this is like over 500 million operations per hour on a single JMS topic. Now, one thing you'll see that even in this graph, all of them are moving together. All the performances are moving together, no matter how many nodes you had, and all the nodes level off about with the same throughput. But there is good news here, as will be seen in the next slide. So the good news is that CPU utilization scales very well across the rack nodes. So in the vertical axis here we have the CPU usage per rack node, and On the horizontal axis, we have the offered load, and you can see the red line, that's for one node. It uses far more CPU than the bottom line, which is for 8 nodes. As a matter of fact, it's a factor of 10. So in terms of scalability of system resources, sharded queues scales pretty well. Now that's the end of the slides of performance that I'm going to show you in this presentation. There are more in the white paper. In 12.1, sharded queues is for the most popular AQ API only. That's JMS 1.0. So some of the other AQ APIs and features that you may be familiar with aren't supported in 12.1. So this is for the thin driver only. There's no PL/SQL NQ, DQ, or notifications that are supported. You can't do array NQ or DQ. There's no propagation, no .NET, no message retention or delay or exception queue, no transactional grouping, and no AQ JMS specific extensions. So the strategic direction, though, is over future releases is to remove some of these restrictions. So keep your eye out as new releases to come out to see how these restrictions have changed for sharded queues. The good news about having so many restrictions is that the API to create sharded queues is so simple. There's only 5 parameters, and most of them are defaulted. And it's pretty straightforward to create a sharded queue. And if you want to convert a non-sharded queue to a sharded queue, assuming that you are using the JMS standard APIs only in your application, what you want to do is empty out your unsharded queue, your non-sharded queue, drop the queue, and then recreate the queue with the create sharded queue, and your application, in theory, should continue to work. Now, we also have a couple other APIs that are specific to sharded queues. That's how we have the APIs to control the streams pool, and how we share it with the Oracle streams if you're using that concurrently with AQ. So I hope you learned something about sharded queues and its new feature in 12c. We're very happy with sharded queues, and we think they're the best database-backed messaging system out there. They've been optimized for the JMS standard. They've been optimized for rack and high concurrency and for a larger number of subscribers. So this is kind of leapfrogs the non-sharded queue implementation. So we hope that if it meets your needs, that you'll give them a try. Thanks for joining us today. We'll be answering questions for another 5 or 10 minutes.